Can you see my screen?
Yes.
Okay. So this is a buckling session. In this lecture, there is no too much difficult theory part. The only two equations you should know how to handle that two equation. So one equation you already use for the some calculations and some derivations, but without any idea how to get that equation. So if you remember that equation, Euler formula, and then there is another equation secant formula. So those two equations, how we can handle, and if you know that very well, so you can do the calculation with the buckling session. So that's the thing. So you should know how to handle that equation, what are the given parameters and other things. So basically we will cover in this session elastic instability and derivation of Euler's formula. So as I told you, we discussed Euler formula in the lecture number 4 or 5. So at that time I told you later we will derive that equation and other thing. So that Euler formula we will discuss. Then adaptation for various end conditions. That means, so you know, buckling will happen when we apply the axial load on the beam. So then it will buckle. So there is a two end on the shaft. So that two ends condition we can change. Then according to that, the buckling condition will be changed. So eccentric loading. So normally Euler formula we can apply concentric loading. So that means the shaft axis and loading axis are coincide each other. But if we change the loading axis little bit from deviate from the shaft axis, central axis, so we call eccentric load. So then we can't use Euler formula. So we will modify that Euler formula. We call as secant formula. So as I told you, there is a two formulas. So you should know how to handle that two formulas. So basically in the buckling, you should know what are the failure mechanisms available with the buckling. So elastic in the elastic instability. So we know with the compression, as I told you, so buckling normally happen with the compression. So it cannot be happen with the axial tensile load or bending it can be, but basically with the axial load. Okay, with the torsion it will not buckle. So are you agree with me? So with the axial load, with the compressive axial load, so then only it can be buckled. So then when we apply the, so I will draw here. So if we have beam like this, so if we apply the axial load like this will buckle. Okay, like this. So this, because these are two end condition. Okay, so with this length of the shaft, the failure mechanism will be changed. Okay? So that's why it's called there is a three ways. So one way is compressive yielding. So that means it will not buckle, it will compressive and break like a tensile yielding. So you know the necking and cup and cone failure. So likewise in here, the compressive yielding means it will crush when we apply the axial load. So compressive yielding, it is one way, and then elastic buckling. So elastic buckling mean when we apply this axial compressive load, so it will bend like this, and when we remove this load again, it will be come to the initial position. And in elastic buckling, you know, there is a permanent deformation like that. But in these two title, elastic and inelastic, there's a further more explanation. So I will explain with the next slide. So normally compressive yielding, it will happen with the short columns. So later on we will call this shaft as a column. Okay, so we will consider vertical beam, so then we call it a column. So that member, that column, if it is short, that means when we consider cross sections and lengthwise, so we call normally cross sections, if it is a circle, we consider as a radius. Okay, so that cross section radius, and the length of the column, that ratio, later on we will call with the specific name that ratio. So if that ratio, if it is very less, we call short column. So that's mean like this. Okay, so this is short column. So this is large cross section with short length. So this is long column, you can see. So this is long column. That LR ratio is very high in here rather than in here. So that length, LR means, L means length, this height, that LR ratio. Okay, so this is called normally shorter column. This is long column. So normally short columns, that means the LR ratio is very less. If it is very less, normally with the axial compressive load, that particular column will be fail with the compressive yielding. If there is a three-way of the failure mechanism, so compressive yielding will be happen with the short column. And if remember that column, if it is long, so then it will be buckle. So if it is thin and long, so then when we apply the axial load, it will buckle like this. Okay. So then there is a if it is a very large, we call it a elastic buckling, because so you can do it at home at that. If you have some flexible thing, so you can apply the load with your hand, then you can see what happened with the that long column. Okay. So not rigid one, but get some soft thing, then you can see the variations, what happened with the axial compressive load. So if it is recover after removing this load, we call elastic buckling. And furthermore, so with this load, when you apply this load, this column will bend and stable like this. Okay, after we remove, it will come to the initial position. So but there's another case, it will not stable, it will break. Okay, so we call inelastic buckling. So with the next slide, you can easily understand what I'm explaining. Yeah, I told you small low LR ratio, because it is short columns, so it will fail with the true compressive. We will measure as a compressive strength. And the large LR ratio, we will consider elastic buckling. And in between these two, that means medium LR ratio, we will consider inelastic buckling. So in here, very high stress apply on this region. Okay. So these are the equilibrium conditions. So with this equilibrium, these three state, we can three conditions we can easily understand with this equilibrium states. Okay. So you know, with this diagram, can you see this diagram? So with this diagram, this is flat surface. So there is a ball. So when you apply some small force, so this ball will be rolled and stable with another position. Okay. So this is kind of elastic buckling, and this is stable equilibrium. So even though you apply this is like uh, curve shape, concave shape surface. So if you apply the load on the ball, it will roll again to that position after remove the force. So that is kind of elastic buckling. In here, you can see when you apply the force on the ball, it will never stop, it will roll down. So this is unstable condition and unstable equilibrium. So this is like a inelastic condition. So with the length of the column, this condition will be changed. So length of the column is the main factor in here. So later on we call it is LR ratio, but keep in mind length of the section is very important. So that this P means a buckling load. So that there is a critical load, it will act as a elastic buckling. So that means at any position it will be stable. So it will never try, it will not try to come to this initial position until this force removed. But in here it will not. It will try to move. It can't stay in this position. This is unstable situation. So in here we call this this load we call a critical load, critical buckling load. Later on we will label these names and other things. And this is the buckling load lower than critical buckling load. This is buckling load higher than critical buckling load. So these three conditions can be happen even the same column with the different load values as well. So if you apply different load value, higher compressive load, so sometimes same column will act as a elastic buckling, even though the LR ratio is less. It doesn't matter, it is less so high. So actually then loading type and loading value, not loading type, loading value of the load, and then the LR ratio. So those are the main factors of the buckling. So do you have any question until this point? Are you there? Hello.
No, sir.
Okay. Yeah, elastic stability. So I'm not going to read this one. I already explained this thing. Okay. So this is the equation. So even though they told us, so we are going to derive this equation, they didn't show you. So I will show you with the lecture note. Is it okay?
Okay, sir.
Lecture note. I will stop the sharing. Then I will share the. So can you see my screen?
Yes, sir.
Okay. So you can see here. So in this page number 4, the lecture note, page number 4, you can, if you have hard copy, you can check yourself as well. So you can see there this with this axial compressive load, this column will buckle, and we will consider half of this column. Okay, half of this column from here. Okay? This is the maximum bending point, buckling point. So we assume this is x equals 0. Okay, so we will measure the length upward directions. So we get as the x-axis. So this is y-axis. So normally we get as a, this is x-axis and this is y-axis. Just assume this, they get as a, this is x-axis, this is y-axis. So this is x positive direction, this is x negative direction. So from here 0 to positive value, and here y 0 and some positive value. You can see when we consider this point and this point, there is a deflections. Okay, not this point, this point in here. in here, okay, in here. So this is the deflection, okay. So delta deflection, and when we consider the any point of this column, the deflection is equals y, and this length L upon 2, because we consider the half of the column, because this is symmetric. That's why we don't want to consider whole column, because this is symmetry. So we can get the bending moment around this point, okay, around this point. So when we consider the bending moment around this point, what is the bending moment? P times delta. Am I right?
Yes, sir.
Okay. P times delta. But when we consider the general point, okay, assume somewhere here. So you can see in here it is mentioned. So if we consider the any point of the column, so we need to derive the common equation. So you can see in here they get the bending moment at this point. So on the column, the anyway load is constant, so it's a P load, and this length, what is the length? Delta minus y, you can see, and this length L upon 2 minus x. Okay, are we clear? So bending moment around this point, P times delta minus y. Now we have some general point, so we can apply, we can substitute here any y values, and we will get the any point bending moment. Is it clear? Are we clear?
Yes, sir.
Okay, so then so I think you know this equation. This is the equation for the standard equation of deflection of elastic curve, so second order differential equation. Okay, this is a if you know, how we can explain. You know the equation for the sigma mi divided by this equation, and in here I is the integral, no? If you know that it is the integral dA. Am I right? Second moment of inertia, normally we will get like this integration, no? If you don't know,
Yes.
tell me. Yeah. So this integrations, so you know, if you have integral, you can get the differential equation in your A-level knowledge. Okay. So in here E come up with the sigma. Okay. So you can substitute here with the E terms in here. Okay. Sigma with the E, and you know sigma divided by the P divided by A E this equation. So using that equation, we can eliminate this sigma part, and then this using this integration, so they will convert to that integral to differential equation. So you, if you want, you can try this one, and you will end up with this equation. Okay, so I'm not going to go through that one. So this is the advanced level thing. Okay, that's right. So converting the integral to the differential equation. Are we clear? Are we, means, so sometimes you will not believe, but you can try out at home.
Yes, sir.
Is it okay? I mean,
Yes, sir.
sometimes you can't believe this one, but this will happen. Okay, so I just gave the clue, so you have integration here, so you can get like this equation. Okay.
Okay, sir.
Okay, so if you have, okay, assume anyhow if you got this like this equation, so you know m, so you can substitute in here m with the the Pn, the buckling load and the deflection values. Then this is second order differential equation. Okay, so you can rearrange this equation. Did you ever solve the second order differential equations? So in your
Yes.
mathematics course anywhere?
Yes, sir.
Okay, so
Yes.
then you know very well. So second order differential equation, if you have, so you can rearrange that equation like this. So in here, y is the function of y is the function. So this is the second derivative of y. This is the y. So if you have dy by dx also in here, so we can put in between these two. But in here dy by dx, then the first derivative is not available, so it is okay. So this is the second order differential equation format. So we can convert this equation, not convert, just rearrange, just expand this uh, brackets, and then you can rearrange this equation. So then we need to solve this second order differential equation. So say, that is also in mathematics knowledge, so you should know how to solve the second order differential equation. So normally it will give this kind of equation will give the sine cos function. Okay. So this is the equation of y. Okay. So we are going to solve the second order equations. So it will give the equation as y equals, so this is the constant value, a b c are constant, and q also kind of constant. So I think you know I think sometime you will forget, but you know how we will get like this equation, no? At least if you don't remember, if you sometimes you don't know, now you don't know how to get the like this answer, but you already learned this kind of thing. If you not, just tell me. Hello.
Hello.
Yeah.
Okay, sir.
Shena and Lahiru, someone named Lahiru. So do you know?
Yes, sir.
Okay. So then so you know, if you have these constant values, so you are the person putting this constant value, so you need to derive that constant values. You need to give the value for the constant values. So then you need to consider the boundary conditions. Okay. So that is the normal nature solving the differential equation. So you know the boundary conditions, and so in this equation, additionally, so this is the equations that you got. So what you need to do, you need to differentiate this equation 2 times to get the d squared y divided by dx squared, and substitute here, and p times function of this equation, and divide by ei and this part, and simplify until this point. Okay, that is the thing in here. Okay, don't worry about that too much. Just substitute this one in here. So earlier we don't know what is the y function. Now we know by the y function. So you can substitute here, and when you substitute here, don't substitute d squared and this part. Okay. So what you need to do, you need to get the second derivative of this function and substitute here, and you will end up like this. And then uh, these two sides should be equal. Okay, if these two sides equal, uh, definitely the sine cos part should be gone. isn't it? Because there is in the right hand side there is no sine cos function. So then what should be happen? So the q minus q squared equal to this part. Okay, so then you can get the q value with the p and ei known value. So now you know the q value and c. So then the q squared, if it is equal to this value, this part goes to 0. Then if left hand side and right hand side, if it is equal, c also should be equal to delta. Okay, now we know c and q values. Now we should use to boundary condition, because there is a 4 unknowns. Normally, you know, if we have 2 unknowns, we should have 2 equations. If we have four unknowns, we should have 4 equations to get the value for the 4 unknowns. But now already we solved the two unknowns. Now we should only need 2 equations. So then we know the 2 end conditions. So one condition is in here, the deflection is delta. And in here, deflection is 0. Or if you consider in here, deflection is 0, in here delta, either. So in here you consider origin is here. So then this at the mid span, deflection is 0. Okay. So according to that, you can read this one, this sentence. So you can substitute that end condition in here in the equations, and you will end up when you substitute in end condition in here. So because you know q and c, so then after substituting you will end up, because sine part will, the a will be 0 and b after substituting boundary condition. Okay, you will get the 2 equation for the from this equation. So solve that 2 equation, you will get the a and b value as well, and then substitute to that a and b and q and c in here. So you will end up like this equation. Sometimes you will not believe. So this will simplify until this point. Okay, and then we have the boundary condition with the y values. The y means deflection. Okay, in here y means deflection at any point. So we know at this end y should be equal to delta. So then yeah, this is the condition. So then that at that point it should be delta, then delta will be cut off. Then cos function should be equal to 1. So then this is trigonometry, so I'm not going to explain that one. So the cos function, you know how to solve the cos function. So you will get the n phi divided by 2 terms, and this is the equation what you have at the presentation. Okay, so in here n means the as a we can consider as a odd number, not even number. Okay, so normally cos 90, cos 270, that values will get the 0, and cos 0, cos 180, those cos phi and cos 0, it will get the answer as a 1. Okay, cos 0 will be get as pi upon 2, 3 phi divided by 2, and 5 phi divided by 2, 7 phi divided by 2, like that pattern. Okay, so you know, if you consider the plane, so normally these two at the y-axis cos will be equal 0. Okay, so this is the function. Now we have the buckling load. E means elastic modulus, I means second moment of inertia, L length of the column. So you can see here the cross section and length of the column and the buckling load are the parameters. The E is material property. So if material is constant, so we don't worry with the material, the E value. E will be the constant value. So normally in here, this equation we can use as it is as well. So, but the n value you should know. That means with the next few slides, you will easily understand what is the meaning of n and other things in here with the buckling. So in here, you know what is the meaning of n, 1, 3, 5, 7. But with the buckling, how we can get the n values, you will understand with the explanation. So this equation we can rearrange like this. Okay. So I will explain how we can get this equation and other things later. So I will move to the presentation now. Yes. Can you see my screen now?
Yes, sir.
Okay. So Euler formula. So you know how to get this equation now. I mean, it was not simple, but now you should at least you have rough idea how we can get the Euler formula. So in this equation, P is load, as I told you, elastic modulus, I second moment of shear area, this length. In here, n means this number of loop you can see here. So if we have one loop like this, we call n equals 1. If we have two loops, n equals 2. So that's why it's in here 4, because n is square. And if we have 3 like this, it is 3 square, 9. So the two ends, the free two ends normally give like this loop. But if we have the free two ends and midpoint, the mid span of the column, if it is fixed somewhere, it can't move anywhere, then you will get this kind of shape. So then you need to consider n as n equal as 2. So in here 2 points are fixed. It will not move with this load. That means these 2 points are fixed to something. So then you will get this kind of shape, the buckling. So then you need to consider n equals 3. Now you know what is the meaning of n in the buckling. What is the meaning of n? So yes, lowest load, critical buckling load. So that is the lowest load of the column. So as I told you, so we will rearrange this equation. If you know second moment of inertia, so that is I we can replace with the AR squared. A means cross-sectional area, R means radius of gyration. Okay, that is very important. Same equation. Okay, this equation. So this equation, the substitute I as AR squared. So R will be put in bottom L square, then A will put in P upon A as a P upon A. Okay. So substitute to I in here. That's all the thing in here. Okay. And n equals 1 in here. So in here, R means radius of gyration. That means, so normally columns cross section, it can be square shape, it can be rectangle, can be then it can be very complex shape. I mean, these are the cross section of this column, cross section, this cross section. So different kind of shape can be. So in this theory, they developed that theory with the standard format. That means even though the column has a different kind of shape of the cross section, we need to convert it to circle. So we assume it is a circle, and we will get that radius. So how we are going to assume that cross-sectional shape as a circle? So those cross-section as an area. Okay. So we need to consider the equivalent area. So if the square shape has a area, assume this is a 50 square millimeter. So we need to consider circle that area should be equal to 50 millimeter square, the equivalent cross-sectional area, and get the radius of that area. That is the meaning of radius of gyration. Are we clear? So if we have different kind of shape, so you don't worry about the area of that cross sections, but you need to get the area and get the equivalent that equivalent circle of that area, and you know what is equal to 5r square, and you know the area of the shape, it should be equal to 5r square, then you can get the radius of gyration. Are we clear, Shana? Fermi?
Yes, sir. Yes, sir.
That is the meaning
Yes,
of radius of gyration. And then, as I told you, later on we call this ratio the LR ratio. If you remember, the very first few slides I explained LR ratio. We call it a slenderness ratio. So normally we don't have the circular shape cross section all the time, but we will get the equivalent circular cross section. Then we have the radius, equivalent radius. So that radius and the column length ratio, the length to the gyration ratio, radius of gyration ratio, we call slenderness ratio. Okay, so keep it in mind. So in here you can see that ratio. This is called slenderness ratio. Okay. Minimum principal radius of gyration, R being the minimum principal radius of gyration. Okay, I hope it's clear. I'm sorry, drawing. Okay, and so the scientists find out, they found out already the standardized ratio, if it is higher than 140, that means that LR ratio, if it is higher than 140 for steel, this is for steel. Normally we are deal with this module, basically steel. So little bit aluminum and titanium, but still the main focus. So the for steel, the standard ratio, that means LR ratio, if it is higher than 140, that means the shorter columns behave differently, and it will be considered as subsequent section. So we are not going to discuss that kind of that means that LR ratio is very high, means we can't use this theory, the Euler formula or secant formula we can't use. So normally check, you will not get the questions with the LR ratio higher than 140, but better if you check the LR ratio if it is above 140, so you can't use this equation. Keep it in mind. Yes, in here the P divided by A means stress, so that's why in here sigma critical. Okay, the sigma critical. In here the we call this LE. Later on we will introduce another terms in here. Okay, okay, so this is the Euler formula function. Okay, the Euler formula explain this one. So if you plot the Euler formula function curve in here with the, so assume this is x, axis, this is y-axis. So curve will be like this. But normally, the actual data of the column, the long column, Euler formula, long column means below 140, okay? The standard ratio, if it is below the 140, and it is, if it is a long column, so we can easily use Euler formula because it is matched with the practical data. But you can see the intermediate columns, it will obey with some extent, but it will deviate after that. But shorter column you can't use Euler formula, you can see. So shorter column normally fail as the yielding, compressive yielding. So it has a sigma y. Okay. So it will not buckle. That's the meaning of here. Okay. So Euler formula we can apply the long column and some extent intermediate column. So this is the explanation here. And yeah, different end condition. With the different end condition, the thing is vary the n value, basically n value. So if you remember in the Euler formula, there is a n terms. It is come up with the cost function, but that n values given by the n conditions. And there is a, if you see here, normally we put as a L here, at the column length, but in here LE, that is effective length. Effective length. So with the n condition, effective length, then n value will be changed sometimes. So that is the thing. So let's see what are the different kind of end condition, the pivot ends and sometimes pin ends, roller ends, fixed end. Those kind of end can be there. So let's see what is the difference there. So I'm not going to read these things. Yeah, you can see here the first one, pin ends. So effective length. So this means in here the 1 degree freedoms in here. So y-axis, the column can be moved along y-axis. So this column has freedom to bend like this without any problem, and it cannot move. The two ends cannot move along the x-axis or z-axis. So then only 1 degree freedom. So that's why it will bend like this. N equals 1, and the effective length is equal to the column length if it is pin end. But in here, the figure B, you can see this is fixed end, and this is again fixed end. That means so sometimes you will feel this is how it will buckle then, because if it is fixed and this one is fixed. But even though this is fixed, this can move like this, but the around this fixing area, this area, you can see this in here, this point also can bend like this, but in here the fixing point, it cannot bend. So it will keep straight columns, little bit I mean little longer, then it will bend like this. This is completely fixed. This is also fixed, but it is fixed to it can, that mean this column end cannot move. 0 degree freedom, this end. Okay, but this column, otherwise how we can apply the axial load? If it is a this end and this end totally fixed, even though we apply the P load, the axial compressive load, it will not transfer to the column. Okay. So this end is fixed, it is freeze like that. So then we will see this kind of bend, but the buckling, but it is not the large loop. So it is a half of this length. That means even though column length is L, the effective length is, so the buckling will generate half of the length. So L effective equals L upon 2. Okay. And in here, figure C, you can see fixed free end. This end is free. That means this is degree of freedom is 3. It can be the move to X, so Y, O, Z directions. Okay, no problem. These directions, and the out of the screen as well. So it can move. Free end, this is fixed. Then it cannot make like this loop. It will bend like this. So you can see it cannot make a complete loop. It will make half of them. That means effective length is 2L then, because this is half. Effective length means how much length may take from the column to make the complete loop. Okay, so this is half. So if we want to complete loops, so we need to another half. That means 2L. Even though the column length is L, we need to 2L to make the complete loop. And then I will get a little bit more time to explain this one. This is very important, that's why. And then fixed pin end, you can see fixed pin end. You know what is the meaning of pin end. So 1 degree freedom to move the pin end. But this end cannot move, so it is freeze. So it will not bend until some extent, then it will bend. And it will make some kind of loop, but it is not the half, it is not the complete loop also. So you can see here, so L effective length equals 0.7 L. So that means this is not a fixed value. Okay, fixed 0.7 is not fixed value. So it's vary with the question. So normally this is the hardest levels in this hardest the questions you can get from this level. Okay, so with this kind of questions you need to consider. So you know, if they didn't provide the value for this curve, how much it will make the loop, like this 70% loop is complete in here. That's the meaning of 0.7. This is 100%. This is 50%, 0.5. So this is 0.7 complete, 0.3 remain. So if that particular questions, if they provide that loop 0.6, so you need to consider that value. But if they didn't provide anything, you can use 0.7. Okay, because that is the thing you learn. So I hope you understand now what is the meaning of effective length. So in these equations, you need to, now we are not going to substitute in here complete column length. So if it is pin end, we can use LE equals complete column length. But if it is different end conditions, you need to consider effective length. With this question, we can easily understand what we explain. This is the material name and use for fixed and pin end. Yeah, as I told you, this kind of condition, fixed and pin end. Column having actual length, that is mean L value 6.5 mm. Assume that the column is initially straight and that is loaded through the centroid of the section. That means we still don't know secant formula. Okay, so we are going to deal with the concentric load. Okay, so centroid of the sections. Determine part A, the standardized ratio. Normally, if you have buckling equations, you need to find out the standard ratio separately. Don't substitute LE and R separately in that equations. Find out the LE, I mean standard ratio, LE upon R ratio separately and substitute that ratio in this equation. So in here they ask that equations, standard ratio, and part B, the maximum mass the column could support if a safety factor of 1 point is specified. So some required parameters given, R minimum and I minimum and area is given this material. So let's see, this is the cross section of the column. You can see overall width and overall height, flange thickness, web thickness, root radius, all the things are given. Moment in initial axis direction, y directions is given. So since the end condition is fixed in the effective length, definitely we cannot consider LE equals as L. So in here they didn't provide that value, so we will consider 0.7. If they provide that values 0.6 or 0.5 or 0.5 means different. See, normally it will be higher than 0.5, 0.6, 0.8, 0.9 can be. So 0.7 L we will use, as I told you. The standard ratio, you can find, first you need to find the LD, then 0.7 times the actual length, 6.5. So then find out the R minimum they provide you. In this question, you don't want to find out the radius of gyration is provided. So then you can find out the standard ratio. The critical buckling load is then this equation. Okay, so in here A put the other side. So area is given 5 and E is given already. Now we know standard ratio. I told you don't substitute in here. So just find out separately and substitute here that LE upon R ratio. And this is the critical load, critical buckling load. Okay. And factor of safety. So if it is a critical buckling load, factor of safety should be PCR divided by P allowable. Normally we need, this is the maximum load it can be achieved. So then this is applied load. So factor of safety they provide already. So we can find out the allowable load there. Factor of safety 1.8. So already we find out the critical load. So this is the allowable load. The corresponding mass is, now this is in Newton. So you can convert to the kilogram or tons, whatever. So then this is the value. So is it clear? It is very simple question, but if you have any question, you can ask. Someone raise your hand. So, Fermi, Sina, Lahiru.
No questions.
Okay. Second one, the structural steel truss members shown below in figure A. So let's see, figure part A. No, the figure A. Are 5 millimeter long and have the cross section shown in figure B. Okay, they are clamped at the bottom and are pinned together at the top. Okay, let's see with the diagram later. The members are free to deflect perpendicular to their plane. Okay, plane, in which case they both end about the cross section axis having the maximum second moment area. If they buckle in their plane, they both bend about the axis of maximum So minimum second moment of area determine the magnitude of the load Q that will buckle the members. Okay. So this is the thing explained here. Okay. So this is a fixed end, and this is pin end, as I understand in here. Yeah. So they explain in here it cannot bend to the out of the screen. Okay. Inside of the screen or something. So the z-axis movements are 0 in here. So assuming like that in this session. Oh no, perpendicular they are plane. Okay, they can. Okay, so that means they can bend to x z direction, and so assume this is x direction, this is y direction. Okay, so don't get as x direction like this and y direction like this, z direction like this. Okay, so I will get the inclined surface as x axis. This is y axis. So inside or outside directions z axis. So it has a freedom to bend any directions. So this is the cross section of the column. So this column of this cross section, this is the, you can see this is hollow cross section. The dimensions is given in here, so they explain in here. Okay, so figure B, cross sections given. Okay, so load Q will apply on here, and the angles, so this is a kind of symmetric. Okay, 45 degree. So when we apply the perpendicular load, it will symmetrically distribute. So it is if it is Q, this is also 45. This is Q cos 45. The Q is then sine or cos. Then if it is equilibrium condition, so if it is in equilibrium condition, that's the load carry on the these columns and this applied load should be equal. That is the theory they use in here. Q equals 2p sine 45. So then p values we know. That means each column carry this load. I told you Q cos 45. This is the thing. Then so we know separately each column how much carry the load. Then calculate the Ix and Iyy. Early in the equations, they provide the second moment of inertia. We don't want to find out that values. In here they didn't provide it, so we need to calculate it. I think you know how to find out the second moment of inertia. This is square shape, so you know the equation. BD cubed. So if we have cross section like this, it is BD. So what you need to do, find out the x direction and y directions second moment inertia. So if it is Ix, so they consider also this is x direction. So you can see the this is square shape, but inside it is rectangle. So the outer surface, it is kind of square shape. The both sides equal, but the hollow shape hole. There is a hole inside. That hole is rectangle. So you can see this is 25. This is 50 millimeter. This is 75. Distance is 75. So you can see if it is solid cross section, so what you need to do, this is the equation of the second moment of inertia. Okay, BD cube. But if it is hollow shape, you need to subtract that part. This is the solid content, and this is a hollow part. So likewise, you can find out the Iyy and Iss. when you consider IXS, you need to consider if it is IXS, you need to consider this is as a B, this is B, this is D, because it's the YY direction, that YY. So you need to consider this is B, this is D. So I think you know these theories. So IXS and IYY you can find out second moment of inertia. Then buckling out of lane. If the buckling is out of lane, then situation is stress will fix free and the effective length is okay. In here, out of plane means it is not bent to the like this. So like this, it will bend to Z axis, towards the Z axis, out of plane. So then it is kind of free end. Okay, fixed free end. The one end is fixed. So we consider only one column in our here. So this fixed free end. So fixed free end. Then effective length, it is 0.5 L. So 0.5 L. So then it will be 2 L. 0 point, because it will make 0.5 loop, 50%. So its effective length is 2L. So then you know P value. One column will carry this load. So you know I Y value. So in here you are not going to find out, you don't want to find out the so equation has a two pairs in here. If you want to, if you know the second moment of inertia, so you don't want to go to the central ratio, another thing. So you just use the equations as it is. So in here you can see EI, YY and 2L square. Okay. So in here effective length you should substitute 0.5 LE. So you can see likewise substitute and you will get the values. So this is the load with the buckling out of plane and QYY value. This is the maximum value it can reach, QY value. And then buckling in plane, in that same XY plane. So it is a fixed pin end. I told you it is fixed pin end. This is in this plane. In this plane, it is fixed pin end. So fixed pin end, then you need to consider 0.7 because they didn't provide 0.7 approximate because we assume that value because they didn't provide. Then same equation, substitute here effective length and same P value, it will not change. And in here IXS, so you will get the QXX value according to that, because P value is given, then you need to multiply by square root 2, then you will get the QXS. So when we consider the QXS and QYY, so this is lower than QXS. The load of the truss is governed by QYY because the lower value will reach easily. So QXS is very high. So to break that the column in XS direction, you should apply the much higher load. But before that, it will break with the YY direction. That is the meaning of with this answer. So you will get the lower value for the QYY. So that thrust will easily fail in the YY direction. So that means you need to consider the YY directions, I mean the YY axis rather than X axis when you apply the load on that particular structure. So that is the comment. So normally when the end exam or as a questions, they will ask this kind of questions and they will ask the comment. So what do you think? What did you think? What do you think with these calculations? Which plane or which axis is more suitable to the? Which one is need to highly consider when we design this kind of structure like that? So you need to give like this comment. So in here you have that comment, but exam you need to think it, no doubt. So did you understand that question also?
Yes, sir.
Okay. In this question also, I'm not going to read. I will just tell you. So you can see in here post, okay, and it will balance with this cable, and there's a turnbuckles. So you will see with the electricity power transmission, so that post also balance with this kind of cable. So there is also this kind of turnbuckle, so they will tight and they will increase the tension of this cable with this turnbuckle. So there is a screw, I mean threads, you can tight that thread, then tension will be increased and this post will be balanced like that. So in here also, due to this tension, so when you apply this tension on this column, so this post trying to buckle because due to these two posts, it is TT. So on the column, there is an angle you can easily find out because you know this length and this length. This is 2.1, this is 2. So if you know that, if you put as a theta, so tan theta equals 2.1 divided by 2, then you know the angle. So then you can easily find out this value t sine theta. Then that means the force carry the 2t sine theta. That is the load, P load. This is equal P. This x component will be cut off. Okay. So then you can apply the theory and calculate the required thing. But they ask, yeah, T allowed. So you need to find out T allowed. Factor of safety is given. So first you need to find out the critical tension. Then factor of safety equals critical tension divided by allowable tension. So after using Euler formula, you can easily find out the critical tension. So you know factor of safety, dividing by that critical tension, you can divide by factor of safety, you will get the allowable tension. So I'm not going to explain each and everything. And in here, I'm sorry again. So this is kind of a fixed end. Okay, this is a pin end. So this is 0.7 L effective length. Then yeah, you need to find out the second moment of inertia. So this is square shape. Force is force is circle. So they need to find out the second moment of inertia with the you know the circle second moment of inertia, 5d to the power 4 divided by 64. So if it is hollow, this is hollow shape, this force is hollow, not solid one, then you need to subtract other part. So those information provided in the equation, so you can easily grab that one. So then critical load, as I told you, so substitute. After substituting second moment of inertia and effective length, you will get the critical load. Then factor of safety, you know, so that you can find out the allowable P load. Then tension. For the tension, you need to use that particular relationship between the force equilibrium. So that this equation. Okay, so in this equation they will put the theta in here, or you either anywhere you can put, but you need to calculate it and find that. So allowable tension is 18.06 kilonewton. I want to mention this important thing. Please highly consider the unit as well. Okay, sometimes you will get the right answer, but unit is wrong sometimes. So if you put the Newton only in here, it's wrong. So the answer unit is very important. If it is unitless, you need to keep it like that. But if it is if it has a unit, you need to mention that unit very clearly. Meter, millimeter, centimeter, whatever the thing, you need to mention. This is the very important thing now. So now we know with the concentric load, I mean, if it is aligned with the center axis, the load is aligned with the center axis, how to do the calculation with the buckling. Now, problem is with the eccentric load. So with the eccentric load, we can't use that one because if the load P load value, if it is deviate from the center axis, we need to modify that equation. So that derivation part, I'm not going to explain, but I will roughly explain how to. So I already explained these things. Okay. So this is the thing. So this is the column. So don't think this is the column feature. This is only column. This is like this column I shape. If we apply the load like this is the center axis, but it has a deviation. So little bit deviation. So due to this P load around this axis, bending available. So bending moment is P times E. Okay, so and if you transfer here, it is PE, bending moment. With the bending moment, you need to transfer here because due to this P load, there is a bending moment. So if you transfer P here, P, you need to put the bending moment as well. So you can see this is kind of eccentric load. So with the eccentric load, you can see this kind of bending can be seen. So now earlier it was only delta. So if you apply the P load in here, so delta deflections you can see. Now delta plus E as well due to this eccentric. So we already derived the Euler formula. I mean, I explain it. So likewise, we can derive that equation as well. But I'm not going to explain this one. So you know how much difficult to derive that Euler formula. So this one also, this one is much more difficult. So this is the equation. So how can I explain? So this part, this P upon A belongs to this part also, but you can see P upon A. This is kind of a, so if we apply the P load in here, so sigma maximum value is equal P, that maximum P divided by A, cross-sectional area, isn't it? So if we apply P load here, so if you transfer, I mean, if you deviate E distance, due to this E distance, this part will come up. Okay. This part times PA. So you can easily understand with this equation, and not easily understand, but you can get some rough idea. So this, when you expand this bracket, so P upon A will come up with 1 plus P upon A times this terms. So this term and come up with this eccentric distance, this deflection. Sorry, this eccentric distance govern this term. If you apply the P load in the correct axis, this is the stress without any problem. So you can get the maximum stress using this equation. That's the thing you need to easily understand in here. I mean, you can get the rough idea with that. Okay. In here, how can I erase it? In here, you can see different terms, EC divided by R square. So later on we will call different, like L upon R ratio we will call central ratio. So likewise in here, this part also we will call with a different name. In here C mean, so E we know what is the deviation from the center axis, and C means the half of the length, so half of the width of the column. Okay, so if the column has a width 5 meter, sorry, 5 millimeter, so 2.5 millimeter is the C. Okay. So if column width, half of the width of the column, so that is a C. Keep it in mind. So R means radius of gyration. So if you know the R and if you know the C, if you know the width, you know C. E normally they will provide. So R, radius of gyration. So you can find out this ratio. And so if you I mean carefully look at this equation, if you can see some confusion. So Chena and Fermi and Lahiru, did you see that?
Yes.
Did you confuse with that equation? I mean, not derivation part. So if assume you know this equation, so do you have any equation with this equation? Fermi, Lahiru, Shana? So normally if you have equations, can you say someone, Shana?
The P over A. This
Yeah,
P
you
over
can
A.
see P over A here and here also. Okay. So normally we are not going to keep same terms two place in the equation, like 2y plus y equals 3 or something. So 2y and y you will simplify as a 3y. So in here PA and in here also PA. So don't confuse with that one. Okay. So this is with in this this is as a square root PA, but we are not going. This is the very important thing with this equation. Okay. So in with this equation you can easily get it. So P over A ratio, I mean that is stress, you will calculate with this sigma maximum divided by this term. So here also P upon A. So don't confuse with that one. So this is the this is already find out the theory developed by that particular persons. So this is explain different thing. Okay, not this is stress. So this is explain the stress, but this is explain different thing. Yeah, definitely P upon A is stress, but with the P upon A divided by E with the square root is give the different meaning. Okay, so keep it in mind. Then yeah, so as I told you, LR ratio means standard ratio, and the EC divided by R square we call eccentricity ratio. So so normally the calculations LR ratio you will calculate separately and substitute to the equation. Likewise, this eccentricity ratio also you need to calculate separately and substitute substitute in this equation in here. And LR ratio also you need to calculate separate and substitute here. So don't substitute here L and R separately, E, C, R square separately. Don't substitute in here. Separate calculations, those things, substitute here. Keep it in mind. Yeah. So this is the secant formula. Yeah, both side equations and both side equation be nonlinear and requirements solving using numerical technique. Yeah. Yes. So I will skip these things. It is very so if we have factor of safety, so factor of safety normally we are not going, so K everywhere you will use. So in here K means factor of safety, you don't worry. So if you know factor of safety, you need to multiply by the applied load or working load, so you will get the maximum load. That is the meaning of here. Okay, maximum load divided by area is the maximum stress divided by that particular, this is secant formula anyway. So if you have factor of safety also, you need to introduce here P, the maximum P as a P, the working load times factor of safety. That is the meaning of K PW. So this is the standard ratio and the stress variation. This is the Euler formula. The central ratio we can apply in this region only. So you can see Euler formula, but secant formula you can apply more than that region. So I show you earlier with the LR ratio, critical stress variations. So we can only apply the below 140 long section and intermediate sections, but not for the short sections. But not, it will not cover the whole intermediate range. But the with the secant formula, it will cover higher than the Euler formula. You can see with the eccentricity ratio, the stress variations you can see in here. Okay. So eccentricity ratio, if it is equal 0, so no, it will match with the Euler equation. Definitely it should be. So in here you can see in this question, I'm not going to explain in detail in this question as well. So in here you can see this post balance with this cable, but in the early question this axis and this cable connect to this axis, but in here that cable connect with this small gadget eyelet, with this eyelet. So you can see this axis and this plane axis is different, so there is a deviation. So this is eccentricity, so we need to use that eccentricity equation, that secant formula, to do the calculation for the buckling. So this equation, that is very well another thing. So that equation rearrange and find out separately all the values. This is E values, D2 that value is given, cross sectional area, and C. So C means this is the width of the column. So half of the width is C. Then second moment of inertia. So this is circular shape. So this is the equation. Then gyrations, radius of gyrations. Then eccentricity ratio, separately calculate. And then effective length, it is 12 because it is fixed pin end. Sorry, fixed free end. Sorry, I'm sorry. This is free end, not pin end. 12. So then center ratio separately calculate, because we know the effective length. Radius of gyration we already know. So yeah, this is the just plot in the variation with the load. If you know the equation, you just substitute the PC value to this equation and find out the different the value for the stresses. With the PC, when we change the PC value, that means the load value, the how the stress from the secant formula variation. So you can see. So and they already so then in here you can't easily get the exact answer. So what you need to do, find out the so you have this equation and you can find out different values, and in here PC value 10.58, because with the sigma y, because we know yield value, yield stresses it's provide. So with the yield stress you can match with these values. So you can see in between these two values it will reach the yield stress. I didn't remember the values. Let me check. What is the yield stress? They provide it. Yeah, 400. 400. So 400. Yeah, should be between these two. That means you what you can do. You can interpolate these values. So and you can get the PC value from these two values, because when you substitute here 5 you will get some value, 10 you will get some value, and likewise you can increase the value of the PC and you will check the stress value. In here you don't want to plot the plot like this, just put understanding they plot in here, but you can check when it's exceed the 400 megapascal. So when it's exceed the 400 megapascal, that means so that particular value, when earlier you substitute value, then interpret those two and get the PC value. So then you know factor of safety, and you can find out the load value, allowable load. So then if you know the maximum allowable load, so you can find the maximum tension on the cable. So in this question I didn't read the question, so they asked the maximum tension. They should ask the maximum tension on the cable. So then just only force equilibrium. Okay, so if you know the PC value, you just get the force equilibrium and find out the F value. That's all. So any questions? Any questions?
Sir,
Yeah.
can you go to the example 6 on the lecture note?
Lecture note.
Yeah.
Okay. Lecture note. Example 6.
Yeah.
Example 6.
Page 18.
Yes. Okay.
Um,
I will check. This one.
yes.
Okay.
Sir, in this one, why don't they use end condition there for this length? Like, why don't they use an effective length? They just take L over R, but for L, they don't substitute an effective length. It's a pin in column, they say.
Let me check. Okay, pin and column. Okay. Your question was why they didn't use LE, isn't it?
Yeah, yeah.
This is pin N column supporters. Other side, the both side pin N or supporters.
It's not very clear there.
Actually, they didn't mention the both end condition. So in here, they consider both end are pin N. Yes. They didn't mention, you assuming it should be 0.7 L. Am I right?
Yeah, I thought it should be
Because you think this is flat surface and it will the, keep it on that surface with the fixed end,
Yeah.
and other end is free of pin end. Okay, anyway, so something like that. But I think they just demonstrate the column without showing the end condition. So they
So
just
here they
mentioned end
don't
condition in
give-
here, pin end column.
Yeah.
So they mention in here in the second line is the L equals 2 meter and is supported as a pin end column.
Yeah.
So the both end they consider as a pin end. Otherwise, it cannot be L equals L.
So here they consider both ends to be
Pin.
pin. No?
Yeah, pin. Then it's fine.
Okay. Yeah, then it's okay.
Any other questions? So so can you see this tutorial?
Yeah.
Can you see tutorial 8? Can you
Yes.
see?
Yes, sir. Yes.
Okay. So I think that this question number 1, it is very, I mean, very similar to the question what we discussed in the lecture, isn't it? Same kind of column, cross sections, and the given values, just substituting another thing. So do I need to explain it? So if you want, I can explain. So in here they consider the pin ends. So that's why LA equals L, I think. Yes. Okay. The pin end. Okay. So L equals L. And this kind of questions. So do you have any questions? Did you try out this question? Anyone? So can you? So if you have the tutorial with you, you have already. I share the screen now, so you can read this question. If you have any difficulty, you can ask. So need I explain it or not? Because it's already near to 10. That's why. Hello.
Okay, sir. Just reading the question.
Okay. Sorry.
So seems like can manage. I was about to do the tutorial after this lecture, so I could understand better. So if there are questions, can I ask it tomorrow?
Yes, of course. Tomorrow also we will conduct that last
Yeah.
lecture. So
Seems like can manage.
others, because I can explain. So if you can, there is no need to explain. No, that's why. Shanal and there was others.
So we'll try it today, and if there's any problem, I'll ask
Yes,
tomorrow.
of course. That's good way because
Yeah.
you have answer with you as well. No?
Yeah.
So there is nothing, just you need to understand what is the critical point. So there is a reaction due to this Q load. This is kind of support column. So there is a reaction. So with that, you need to deal with that. Okay. So that's all. But don't look at the answer first. You can try out yourself first. Then only you can understand what is the difficulties with you. Okay.
Okay,
Then you
sir.
can look at the answer. Then that's the way. The next question is nothing. It's just the relationship between the circle and square shape and triangles, and get the radius of gyrations. Okay. So I told you even though there is a different kind of shape of the cross sections, you can get the equivalent area with that equivalent area give the radius. That radius called the radius of gyration. So that value and the relationship will learn. And this is similar to example what we discussed earlier also with the you need to force balance equilibrium and find out. So this kind of question you need to mark the force available in here first, then identify the where you need to do the so which one is buckling conditions. So in here I think this one is will be buckled. I don't know, I didn't read it anyway. So you can see in this even though this kind of questions the calculation is very little. So you mean thinkability is the higher thing, I mean critical thing in here, not the calculations. So can I wrap the session now? Any questions? Shana, do you have any questions? If you have the question about tutorial, you can ask tomorrow definitely.
Yeah.
For me, Rahul?
Now, no, sir.
Okay.
No questions.
Okay. Okay then. Thank you and good night. So,
Good night, sir.
tomorrow I think
Yes.
4 p.m. No? We will do it.
Yeah. Yes.
Okay. So tomorrow session it will be large session. So I will not try to get the long time. So can you do me a favor? Uh, so if I explain, so sometimes if you know these things, can you tell me we know, so can you skip this part or something like that? Sometimes I feel if you don't know I need to explain something like that. So tomorrow sessions will be take I mean it's a large session. So if you know that thing and if you understand it, can you give me the commit like that? Okay, so we understand it. Can you go that skip that part or something like that?
Okay, sir.
That will be better. Sometime I will explain something you know already, so then it will be boring also. Something.
Okay, sir.
Okay. Okay. Good night.
Okay.
Good night,
Thank you.
sir. Thank you, sir.
Thank you.